So that was a side note, and let us come back to our main discussion. So let's recap. Our discussion so far brought us to this point that any wave function at a given time can be written as a linear combination of, say, the energy eigenfunctions. Now, remember that we can choose the energy eigenfunctions in such a way that they form an orthonormal set, meaning that their inner product will be given by something like this. So how can we suppose that we are given phi? How can we express phi in terms of psi? In other words, how can we find this constant Ci? So what we're assuming is that we have the time-independent Schrodinger equation and we have solved it somehow. So we have solved it. So what we have found is that we have found all the Ei's and the corresponding psi i's, degenerate or not. And then we've been given a particular state, phi of x, and we have to find out how to express phi of x in terms of this set psi I. In other words, how to find Ci. So to do this, what we use is that we use the fact that we have the psi i's have been normalized and they are orthogonal. They form an orthogonal set. There's a subtlety in making this an orthogonal set when EI is degenerate, but we are not going to gloss over that and come back to it in a later lecture. So to find out what phi of x is, what we do is that we use the fact that C of I, or let's say C of j, is given by psi j, the inner product between psi j and phi. So let's prove this statement. So we start with psi j phi. Now we are assuming that this inner product, which is an integral, converges. So what we can do is that we can express phi as a linear combination like this. So here I get I, Ci, psi I. Now because the integral inside the inner product converges and this sum is also assumed to converge, we can reverse the order of this integral and the sum. In other words, we can take the sum outside the integral. And if I do that, then this is what I should get. But then what is this thing? This is nothing but our Kronecker delta function, or a Dirac delta function in case the energy eigenvalues are continuous. If that is the case, then this is going to be I, Ci, delta of Ji, and therefore if I do the sum, then what happens is I get C of J, which is exactly the statement that we wanted to prove. Okay, now that we have figured out a way to express any arbitrary function in terms of the energy eigenfunctions, we can now answer the question, like if I give you some initial state at some time t0, what is the state of the system at a later time? If I take the energy eigenfunctions and look at their time evolution, the time evolution is just given by the spatial part times an exponential part, like this. Now, remember that, so this is a solution to Schrödinger's equation, the time-dependent Schrödinger equation. But remember that Schrödinger's equation is a linear equation. So if it's a linear equation, any solution of any linear combination of its solutions will also be a solution. Therefore, what we can say is that, since phi is a linear combination of psi at time equals to 0, it must be that this is also a linear combination at later times. Or in other words, this is given by the spatial part times the exponential part. And this is a very powerful result. So what it's saying is that if I solve the time-independent Schrodinger equation, then I have essentially solved the problem. Because if I solve the time-independent Schrodinger equation, we know how psi I evolve in time. They evolve very easily. They just evolve by an exponential factor, because if you just integrate this equation, that's what you get. And once you get this, using the fact that any old state can be expressed in terms of linear combination of the eigenstates, you can evolve it in time, and this is the result you get.